Biological neural circuits are masterpieces of efficiency. Shaped by metabolic and material limits, they learn codes that are diverse, sparse, and robust. Modern deep nets, by contrast, often overfit to abundant data and compute, building redundant features and missing long-tail events. So here's the question. Can we bake a formal resource principle into artificial networks to get the same kind of robustness? One interesting theory from Barber and Lichtman at 1999 found during the neural development, which a neuron's finite metabolic budget induces a trade-off between firing rate and audience size. If a neuron talks a lot, only a small audience should remain. If it's usually quiet, then everyone listens when it speaks. Think of seeing a snake at home. It's a rare cue, so the snake neuron is usually quiet. But when it fires, every downstream unit should listen and react. We formalize this cost as a neuron's traffic, the product of how often it speaks and the size of its audience. We'll show this on a tiny network. We start fully connected. During training, most signals hit the blue hidden unit, so its activity grows more than the green one. These are two different controllers that may work independently. First type controller is setting on fan-in, when we zoom in on the inputs to each hidden unit. Thick lines mark stronger influence. Under a fixed budget, the blue unit keeps just one input, while the green unit keeps three. We prune the weak links and update the left mask. This is what we called reduce activity. The second type is setting on fan-out. Same rule. The talkative blue unit keeps a tiny audience, and the quieter green unit keeps a bigger one. We prune again and update the right mask. This is what we called reduce broadcast. When a connection is pruned, we set its mask to 0, but we do not delete its weight or its learning signal. The parameters, their moving averages, and potential gradients are retained. The mask is a routing gate for traffic, not a permanent cut. This matters for regrow. As activity shifts, previously masked edges can come back if the budget allows, or if they become competitive. Now we keep training from the pruned state. Pulses travel only along the edges that survived. As activity shifts, each neuron reevaluates its top K audience under the budget. If a previously masked edge becomes stronger than the weakest kept edge, it replaces it. This is competitive and reversible. Over time, this keeps overall traffic in check, cuts redundancy, and spreads capacity toward rarer, more informative features.